Hello everyone, today we will discuss a new topic, collapse or collapsible soils, which is related to unsaturation of soils, and some soils they exhibit collapse due to saturation. So today we will discuss about that. Before discussing the collapsible soils and collapse behavior of some soils, let us discuss what we have discussed in the previous lecture. In our previous lecture, we have gone through the swelling mechanism or swelling behavior of some expansive soils, the swell potential which is exhibited by some expansive soils as due to wetting, the underlying mechanisms we have dealt, and also we have discussed the measurement of swelling pressure of soils due to wetting and during when the volume changes are restricted. So, swelling potential is observed when the volume changes are allowed, and swelling pressure is measured or swelling pressure is exerted by the soils when the volume change is restricted. Let me briefly mention what are the different techniques we have used for estimation of swelling pressure in the laboratory. So, the swelling pressure can be estimated using a conventional consolidation test, which is swell and consolidation test. Under swell and consolidation test, we have seen that when you plot the EEP curve, the void ratio and pressure curve or load, under the compression, initially the soil is at compacted state or any other state, but at dry state which has a void ratio of this much under a sitting load or sitting pressure, and this is a void ratio at dry state, and when the soil is saturated, so it swells, and the final void ratio at equilibrium is E naught, and when this is consolidated, this shows this behavior. So, if you extend a straight line, horizontal line from the initial dry state, then corresponding pressure is called swell pressure, because swell pressure is the pressure exhibited by soils when the volume change is restricted or volume change is 0. So, when the volume change is 0, so it should be same volume or same void ratio, then it is E dry, then corresponding pressure is called swell pressure. So, this is swell under consolidation, this is swelling, and this is consolidation, swell and consolidation test. And the second method is method of equilibrium void ratios. So, in this technique, series of tests are conducted on duplicate samples at different loadings. For example, this is the initial void ratio, initial state at dry, and when the soil is compressed in the initial state itself, the compression line is this, and at any given particular point under any given particular load, if this is wetted or saturated, then it exhibits some swelling behavior, and as the load increases, this is sample 1, and another sample at different void ratio, if it is wetted, the exhibited pressure would be smaller, and at any given higher than this particular load, this may be smaller than that, which exhibits a collapse. So, when you draw a straight line connecting all these points, and when you extend this a horizontal line from the initial void ratio, wherever this cuts, that is the swelling pressure. This is the second method, and in the third method, a constant volume technique, which is popularly used. In the constant volume technique, from the initial state, the soil is wetted and it tries to swell, you load it. So, you increase this much of load, a small load increment is done, and so it tries to compress, again it will try to expand or it will try to increase its volume, then you apply another load. So, essentially this will be like this. When you extend a horizontal line from the initial void ratio, this is how the curve is, and it stops increasing its volume when the maximum applied pressure on the soil is equal to the swell pressure. So, it is observed that this is the strain that is allowed in the system would influence the estimated swelling pressure. If the strain is smaller, the estimated swelling pressure is higher. So, essentially the loss in the energy is minimal, so it would estimate a correct value of swelling pressure. So, recent days the test is conducted on odometer sample or any other sample. So, you have a porous stone, porous plate at the top and bottom, and you have the soil sample. Now, you have a top plate, on top of it a load cell is attached. Like this, and either load cell or directly you can attach a proving ring. And when this is connected to a reservoir, when the water is allowed to enter into the soil sample, then the soil tries to swell, but this the load cell which is connected to the load frame would not allow any volume change to take place, but this load cell or proving ring will allow to record what is the reaction that is exerted by the soil. So, from this you can estimate what is the swelling pressure that is exerted by the soil mass, and that would be more accurate. So, these days the swell pressure versus time is plotted. So, the swell pressure will increase with time and reaches an equilibrium value, a maximum value that is at equilibrium. So, this is corresponding to the fully saturated state. So, this is often estimated these days. Further, the suction controlled swelling pressure data and by varying mean stress, how the volume changes under a suction controlled environment. These tests are conducted to determine the constitutive surfaces in load, suction and degree of saturation or water content. In this surface is plotted, that is often done in these days. So, that could be plotted in this manner. This is a strain axis, or it could be void ratio also, or volumetric water content, and you have matrix suction UA minus UW on x axis, and this is another axis epsilon y, and you have another axis that is sigma n minus UA. This is net normal stress minus air pressure, net normal stress. The net normal stress versus strain plot, we know as the net normal stress increases, the strain value decreases. This shows this kind of a behavior, and this is a typical consolidation plot. So, as the loading increases, the strain value decreases. So, if you unload the sample at any given point, this is unloading plot, and this is loading. Similarly, initially the soil condition is this at fully saturated state, and when you load it, so the volume of the sample decreases and the strain value decreases with increase in the load. But here at the same condition, whatever we have considered earlier. So, if you increase the suction without any mean stress, then you observe that this also exhibits similar behavior. This is also called loading. This loading is a suction loading. So, when you increase the suction, the water content decreases, so the volume of the soil decreases if it is an expansive soil. So, this is a loading curve, and if you wet it at any given point, so this exhibit this behavior, this is unloading. So, this kind of a surface you obtain, this is a surface you get for different combinations. To obtain these surfaces, the tests under controlled suction are conducted, and we should be able to vary the mean stress, net normal stress, and UM suitably should be controlled too, and we should be able to measure the volume. Then we can obtain this kind of a surface, we can build this kind of a surface, and which would help in understanding the soil behavior at any given point, especially the expansive soils. The volume change behavior of soils can be estimated under suction and net normal stress environment. Coming to the earlier observation that when soil is loaded, this is void ratio and this is stress. So, this is compression line. When the soil is wetted under particular normal load, soil may exhibit swelling, and at very high loads soil may exhibit decrease in volume or collapse, as I mentioned earlier. So, this is the case with expansive soils exhibit swelling under loading less than swelling pressure, and under loading greater than swelling pressure, if we wet the expansive soil, it will exhibit decrease in volume. Generally this is called collapse. However, there are some soils that exhibit collapsible behavior. So, the characteristics of the collapse come from the physicochemical nature or some mechanical forces that exists within the soil structure. The characteristics of these collapsible soils we will study now. A soil called loess. Loess is a widespread hyaline deposit which is considered as collapsible soil. Loess is found in many countries such as North and South America, Russia, Europe and Central Asia, China and many other parts of the world. So, the loess soils are deposited by wind deposited soils, and interesting part is that they consist of silt sized primary quartz particles. From the cold weathering process they have formed, and glacial grinding processes they have they came into existence. It mainly consists of irregular shaped silt sized these quartz particles, and some clay content also exists within this loess soil. So, these silt sized particles are deposited in fluvial transportation due to retreat of continental ice or glaciers, and so some silt particles they were deposited along the floodplains of rivers. There is a fluvial transportation and due to retreat of continental glaciers. So, the silt is sorted by fluvial action and is redeposited by wind action. So, further feldspars, micas and carbonates and clay minerals are also present. Along with the primary quartz particles. So, they form open structures. So, this is how they form. If this is one sill sized quartz particle, and these are the clay particles which are surrounded or accumulated around the sill particle, and this is the conglomeration of or aggregate of several of these sill particles. Which I represent with dotted lines. So, this is one aggregate. So, such several aggregates would form as open structure like this. So, these dotted lines indicate an aggregate like this. So, these are individual aggregates. These are called micropores, and this is called macropore. Generally, these kind of soils will have dual porosity, one micropore and macropore. So, the increase in the load on the soil will only decrease the macropore volume. So, the micropore volume nearly remains constant. So, here individual particles are or individual aggregates are attached by several forces that we will discuss now. So, there are several bonding mechanisms. One is van der Waals forces. These are the van der Waals forces are between quartz particles making the fabric structure. So, two individual quartz particles, this is one quartz particle and this is another quartz particle, they get attached due to van der Waals forces. The second, there could be chemical bonding. So, the ionic variability of surfaces of the quartz particles facilitate attraction of charged clay platelets. This is chemical bonding. So, when the charged particles, so when there is ionic variability on the clay silt particle, and clay particles are attracted, this is another particle and the clay particles are surrounded. So, now when there is some moisture that is available, general atmospheric conditions, clay platelets absorb moisture and then retain some moisture, which is called hygroscopic moisture content. So, that when the hygroscopic moisture content exists, there is a clay bridge that form between these two particles. And the third force could be suction or negative pore water pressure. As the water content is only very small, the amount of water that is present at the natural atmosphere is very small compared to the total volume of pores that exist. So, there is a negative pore water pressure that exists, and suction values are very high in this particular soils. And there could be carbonate bonding. So, this carbonate bonding is between different quartz particles, and other salt bondings like gypsum etc. also may present. The low soil can also be artificially made because the essential form of structure, that is open structure, that exists in the soil. So, open structure is, as I showed, so this is individual aggregate and this is another aggregate and this is another aggregate and this is another aggregate. So, individual aggregates will have several of these quartz particles that exists with different bonds, and there is another bond between the quartz particles here and then the next aggregate. So, under application of the load, the macro volume would not collapse, only the small amount of macro volume may decrease, because the bond between different aggregates is very strong and the applied load will not cause any damage to the macro pore volume or damage to the open structure of the loose soil. So, now as the forces are known, because there are silt sized particles and clay particles, different combinations cause the open structure, the loose soil can be made artificial in the laboratory. So, this is attempted by several researchers by considering ground silica, which is passing through 75 micron sieve or 63 micron sieve, and which is mixed with different proportions of clay in oven dried state, and this is deposited. The way the loose soil deposit due to wind action, the soil is kept in a sieve and deposited onto a surface by maintaining a gap of 200 mm by what is called airfall method. And the soil is deposited here, and this soil, which is now sprayed small moisture, so that to artificially facilitate clay bridges between the silt particles, and this is how naturally it exists. So, this after spraying some moisture, and the structure of the loose soil may become open structure like this, and then studied using collapsible tests. In odometer it can be studied, where in the odometer under two porous stones, the soil is initially compacted at particular density, and then load plate is attached. On top of it, the loading is applied, and this is connected to a reservoir, and the moisture is allowed to enter. Now, EP plots can be plotted. So, here, so this is the initial condition of the soil. So, now when it is compressed to one particular loading, so this is the loading level. Then here, when the soil is wetted, soil collapses. So, this is the collapse potential or the collapse. Now, if you consolidate, so this is how it shows. This is consolidation, this is compression, because this is air dried state, and this is a completely saturated state. So, under a particular load, it is observed that soil will collapse, the volume will decrease. So, expansive soil under this particular loading, when you saturate it, the volume will increase or void ratio will increase, but these collapsible soils will decrease its volume. So, essentially because as soon as the soil is saturated, so there is a initially the clay bridges that exist between the silica particles would start breaking, because the suction is absent now. So, suction is essentially goes to 0. So, now the bridging formation is gone. So, this whole structure will collapse. So, now the aggregates will collapse and all the silt particles would crumble into aggregates like this upon saturation. So, initially you have micropore volume and macropore volume. After saturation there is no two different pores would not exist. So, because of the loss of suction within the soil structure which supported the open structure until it got wet. So, that is the collapse, and under different particular loadings also this can be studied. So, the soil is initially somewhere here. So, if this is compressed, this is how the volume decreases. So, this is compression. So, when it is wetted, it exhibits minimal collapse, and as the loading increases, the collapse will increase. Something like this. So, this is collapse under different loading. So, this is very well studied. Essentially, if the building is constructed on such kind of a soils, collapsible soils, in dry state, whatever the loading you apply, the change in the volume is negligible. It does not exhibit much volume change. Therefore, we consider that this is safe. But however, under the same loading, when there is a sudden ingression of water into the soils due to floods or maybe due to intense rainfall, then a sudden collapse of the soil structure causes a macroscopic collapse behavior or volume decrease behavior we observe, and entire building can sink into the ground. On the other hand, if the building is constructed on expansive soil, if the building pressure, the exerted pressure from the building load is lower than the swelling pressure of the underneath expansive soil, then the saturation or wetting of the underneath expansive soil causes increase in the swell potential. The entire building can get uplifted due to the swelling nature of the underneath soil. So, there are other clays such as kaolin, which contains kaolinate mineral, so which is rich in kaolinate mineral. The kaolin clay is also found to be exhibiting collapse behavior. This is observed very recently, because the kaolinate mineral has silica and alumina units attached. In this manner, several units are attached. In this manner. So, the basal spacing, this distance is around 0.723 nanometers. So, this is a silica sheet, this is alumina sheet, which are attached in this manner, and each basic unit is attached to the other basic unit in a strong bond. So, this is basic structure of the kaolinate. in a three-dimensional manner, if you visualize, the silica contains 4 oxygen atoms, so in between you have a silicon, O2 minus, these are oxygen atoms. This is basic silica in a 3D view. This is silica, this is 2D and this is 3D. And similarly, alumina, you have 6 OH minus are available. These are OH minus hydroxyl ions. So in between you have alumina, Al3 plus, this is OH minus. So this whole thing is called alumina. You have aluminum here and you have silicon here. So this is alumina in 3D view. So in 2D view, this can be visualized as 6 hydroxyl ions, and in between you have alumina. So in 2D view, if these two are combined in 2D view, the silica and alumina are combined, so that can be represented as these are 2 silica and this is alumina sheet. This is how they got attached. So this is one silica, another silica, and this is alumina, and this is one silica, another silica. So this is the whole unit. So this is 2 silica and 1 alumina. This whole thing is represented in this manner. So these number of sheets, basic units are attached and it forms the kaolinite mineral. So kaolinite mineral, when it is represented with sheets attached, this is one particular sheet of silica and alumina, and you consider number of sheets those are attached in this manner. This is a basal plane or surface. You have termination sites here, O2 minus on silica face. On the other face you have alumina face, where you have termination sites as OH minus. Similarly, at the edges you have both O2 minus and OH minus. So on alumina face you have OH minus as termination sites, and on silica's face you have O2 minus termination sites. And because of these termination sites, and they acquire charges under some particular pH environment, and this causes changes in the structure of the clay soil, and which causes collapse under wetting. This will be explained now. And if low soil collapse nature is due to some mechanical loading, is due to wetting phenomena under loading, which is similar to some mechanical behavior. But here the collapse behavior of kaolinite is purely due to physicochemical in nature. So, physicochemical because the changes in the charges on the clay surface and the edges result in different associations of particles like edge to face to face, etc., which is macroscopically seen as collapse of the soil. Let us try to understand this by understanding what are different charges that exist in the soil. So, on basal surface of silica, basal plane or surface of, there is face, that is this surface. Always contains a net negative charge. So, this is acquired due to isomorphous substitution, which is a permanent charge to the clay platelets, but this is insignificant because specific surface area is so low. This is insignificant value in terms of magnitude. So, because surface area and cation exchange capacities are very low, small. On the other hand, the clay acquires pH dependent charges. So, this is a pH independent charges. So, this is due to reactive termination sites on the surfaces and alumina basal surface, alumina face and edges cause these reactive surfaces are reactive alumina face and reactive edges cause pH dependent charges. So, these pH dependent charges come from protonation and deprotonation of alumina sheet. Protonation and deprotonation of alumina on edge and protonation and deprotonation of alumina on basal plane, basal surface, and deprotonation of silica sheet on edge. So, essentially the protonation is the adsorption of H plus ions onto the surface when the pH of the environment is very low. There is an abundance of H plus ions. So, H plus ions will be adsorbed onto the surface, then it acquires positive charge. So, deprotonation means it releases H plus ions from the surface when abundant OH minus ions are available in the solution. So, that means with very high pH values, so the deprotonation occurs due to release of H plus ions from the surface. So, deprotonation, that is H plus acquiring H plus ions or releasing H plus ions, causes different charges to the surface and edge. So, the pH at which the surface charges are changed and pH at which the edge charges are changed are two different. That makes it too complex to understand how these charges would change. So, this is commonly understood using isoelectric point. called IEP. So, generally this is defined as the pH value at which the clay particles isophoretic mobility or zeta potential is 0. So, if you consider the clay platelet to be like this, which has a negative charge on the surface, this is the diffuse double layer around it. So, due to changes in the pH environment surrounding this clay platelet, so the diffuse double layer thickness would vary, change. So, when the charge negative itself gets 0, so the charge on the surface is close to 0, so the zeta potential, which is this is less than the actual diffuse double layer thickness. If this is the diffuse double layer thickness, the zeta potential is considered to be very small, somewhere here. So, zeta potential is considered to be where isophoretic mobility. When the particle is moving, there is a shear resistance or shear force that exists on the surface, and because of which whatever the charge that exists on the around the particle, there is some film. Due to diffuse double layer, there is a this much film would exist around it, but the particle is in motion due to some electric current. So, due to the shear force, the thickness of film that exists around clay platelet would diminish or reduce, and the charge on this particular film under motion is called zeta potential. Essentially, isoelectric point would indicate where the charges are essentially 0 at that particular pH. So, the IEP of edge is different and IEP of face are different. So, generally IEP of edge is between 5 to 6 and IEP of faces are much higher. Generally IEP of edge is 5 to 6. So, when the pH value of the solution is less than IEP of edge, so generally the clay surfaces, due to isomorpho substitution, the silica surface will have net negative charge, face has negative charge, and edges carry positive charges. So, because the pH value is less than the IEP of edge, because the pH is low, so it adsorbs H plus ions onto the surface, and which results in positive charge on the edge. So, due to the negative value on the face and the positive value on the edge, so it has edge to face flocculation. So, this is edge, and this is face. So, this kind of a structure forms when the pH value is less than IEP of edge. When the pH value is greater than IEP of edge, where face is negative and edge is positive, so which results all are negative. So, therefore, it results into dispersed structure like this. So, face to face arrangement. So, this is called face to face arrangement, and this is called edge to face arrangement. So, the clay platelets would get arranged into either edge to face or face to face arrangement depending on the pH of the environment. So, therefore, if I consider a volumetric flask where if I pour clay sediment they assume this kind of a structure, edge to face, and the volume of the sediment would be highest. This is volume of the sediment. This is when pH of the solution is less than IEP of edge. in the same volumetric flask, same clay is poured, but the pH environment is such that pH is higher than IEP of edge. It results in very low volume. So, because particles are dispersed in nature, this is the sediment volume. So, that is the reason why when the kaolinite is mixed with kerosene, the sediment volume is higher compared to pure distilled water. That will have pH of around 7, so which is greater than IEP of edge. So, particles will be in dispersed state. So, therefore, the volume will be much lower than compared to kerosene. So, therefore, the swell potential when it is calculated as volume of sediment in water minus volume of sediment in kerosene divided by volume of sediment in kerosene, which is a negative value less than 0. So, the negative value indicates the behavior. So, when this kaolinite is tested in the odometer, the collapse test can be conducted where the void ratio and P load or stress, mean stress can be plotted. When the soil is compacted at one particular compaction density, and when it is loaded, which exhibits this behavior, when this is wetted, this suddenly collapses, and when you consolidate, this curve goes like this. So, this is compression and this is consolidation, and this is collapse. Which is plotted as collapse potential versus time. It starts from origin. So, the collapse potential increases with time and reaches an equilibrium value after certain time. So, this collapse potential is nothing but change in void ratio divided by 1 plus initial void ratio. That means, this is the E naught and this is delta E. This delta E by 1 plus E naught is the collapse potential. This collapse potential will increase with time as soon as this is the point where it wetted or inundated. So, it changes with inundation pressure again. This is one particular inundation pressure, but with change in the inundation pressure, this collapse potential also vary. So, the kaolinite clay also exhibits collapse behavior similar to loess soil, but in the loess soil, because there are several different particles like silica, that is silt sized quartz particles, and clay particles surrounded by them, and which forms bridges around the different silica particles, which causes open structure, and this gets collapsed as soon as this is wetted or saturated. In case of kaolinite, there is open structure because of the different charges on the face and edge, and this causes open structure formation in completely air dried state. As soon as this is saturated with pH solution higher than IEP of edge, then the charges on all the surfaces and edges will be same, which causes collapse of the soil. So, the collapse nature of Kaolinet soil is purely physicochemical. Thank you.